Hello, this is problem 7 from the first problem set of David Tong's lecture notes. So this is our Maxwell Lagrangian thing, and we're asked to show that this is invariant under this gauge transformation. So our A mu's will go to A mu plus D mu of some scalar field of, this is xi? Is it? I don't know. It's squiggly. It's a scalar field. I'll just call it squiggly thing. So that's very easy to do, actually. So if we just take our individual f mu nus and we plug in this expression for A, we will quickly find that we get these four terms, and then we have these two terms that are the same because we can commute partial derivatives, and so they cancel. And so our electromagnetic field tensor is invariant under this gauge transformation. And so correspondingly, our Lagrangian is invariant. So now we can move on to it asks us to find the energy momentum tensor. And that will just be our usual equation down here. And we can use the fact, so I already went over, we found the equations of motion for this Lagrangian, and in doing that you calculate dl d mu a gamma, and that we found to just be minus f mu gamma. And yeah, so we just plug that in, and we plug in our Lagrangian, so we're left with this. And so we can note that it is not symmetric. So this term is symmetric because of our delta function, but this term, if we exchange mu and nu, yeah, it's just clearly not going to be the same thing. So it's not symmetric. And it's not gauge invariant. So all of our f's are gauge invariant, but then we have this term here that, clearly when we make this substitution, we're going to get some extra terms in this, and there's nothing to cancel them, so this expression won't be gauge invariant either. So now we can redefine, we can define a new energy momentum tensor like this. And so I can writing it out, we get this, and the term that we've added is similar to our original term here. So we have them both, and I can play around a little bit. So with this term, I can use the antisymmetry of f. So switch the gamma and the mu, so I get a plus sign. And then both of these terms will have an f gamma mu that I can factor out. And that'll leave me with a d nu a gamma minus d gamma a nu. But that's just f nu gamma. So our new electromagnetic field tensor, our energy momentum tensor will be this. So it's entirely composed of our electromagnetic field tensor. And so it asks us to prove a few things about it. So the first thing we'll do is that it's prove that it's traceless. So to calculate the trace, we just sum over the diagonals. So we want sigma or theta mu mu. So just plug in, changing nu to mu here, and summing, we get this expression. But this, so summing over the delta function, or the delta, the Kronecker delta, summing over its diagonals, it's just 4 ones. So we get a 4, and that cancels with this 1/4. So we're just left with f alpha beta, f alpha beta. And then this term is almost the same as this, only the summing indices are different, but we can exchange gamma and mu in this term, or this term, whichever, it doesn't matter. And then it's just the same thing, doubly contracted electromagnetic field tensors, only we get the minus sign. So they will cancel and we'll get 0. And then we want to show that that this is actually conserved. So if we calculate the divergence of this, we'll get, so if we use our original expression here and calculate the divergence of that, we'll get d mu of our original energy momentum tensor minus d mu of this term. But our original energy momentum tensor, of course, is conserved because we derive that from this expression, which we have already shown is conserved. So that's just 0. And then we have this term, which we'll have to do with product rule. So the first term looks like this. Derivative is acting on f gamma mu. And then the second term, we have d mu d gamma a nu. So this term, the equations of motion, if you remember, were just d mu f mu nu equals 0. So this is of that form. So this is 0. So that term goes away. And then this term, we can play our game, or this is our f is antisymmetric, and then we have two partial derivatives, so it's symmetric between mu and gamma. So we can play our game with the indices and show that this is equal to minus itself, and so it is also 0. So this new energy momentum tensor is also conserved. And we also are asked to show that it's gauge invariant, but since it's can be written entirely in terms of f, and we've already shown that f is gauge invariant, then of course this is gauge invariant.